Hey everyone, today I'm gonna show how to do mathematical functions in Blender. This is an add-on that I wrote long ago, but I transferred it to work on version 2.9 and 3.0. I know there's a similar add-on that comes with Blender, but this one, when I did it, I didn't know it existed, but it has some extra functionalities, so I'm gonna be showing those as well. Alright, so the way to install this is that you wanna go into this link here, this GitHub link. Once you've done that, then you're gonna and I'll put it in the description. Once you've done that, you want to go to releases, and then if you're using Blender 2.8 still, you would want to download this first one, but in general, if you're using 2.9 or 3.0, you would go ahead and download this zip file. Once you downloaded the zip file, then you can go ahead and install it in Blender. And you're gonna get an error until you install SciPy in your specific Blender release. So the way to do this, and this can be done in other in Mac or Windows as well, is that you want to go to whatever the Blender zip file that you use, or the binary. So to do that, mine in this case is in this folder. So I'm gonna be using this 3.0 alpha release that I downloaded. So this is basically, if you look inside, it has this is what a usual Blender zip file would come with, like after you extract it. And then inside of there, where you want to go, it's you're gonna go to the folder 3.0, and then you actually want to go to Python. So you would actually want to go to Python, and then once you're in here, you're gonna go to the binaries. And then once you're in here, all you have to do is do two commands. So the first command, and these commands are you can find in the GitHub as well. So the first one is gonna be Python -m ensure pip. That just oh, and in this case, it's not. You have to look for the executable you have here. So in this case, it's Python 3.9. So you have to change this. This is just making sure you can install packages, and then I already installed SciPy, so I'm not gonna do it at this moment. But the other command to install SciPy, and make sure you are in this directory, otherwise it's not gonna work, is gonna be Python 3.9 again, -m, and then pip install, and then in this case the one library we need is SciPy. So after you've done this command, then SciPy will get installed in your Blender release, and then that's all you need. After you've done that, you can go ahead and open Blender. And when you open Blender, and after you have to go to edit preferences, install, and make sure you grab the zip file. So I have it here, Blender math. Then you would go ahead and install it, but I already have it installed. As you can see here, it's already installed, version 1.2. So this the way this works is that we're gonna go here, and we're gonna go to add mesh, and then we're gonna find these three options here. So if we start with X, Y, and Z, this is some default functions that we have. So the way to change this is that you want to press F9. That way you get this menu if it disappears. If you do any other action, the menu is gonna disappear, and you're gonna have to add an object again. But since I haven't done any action, I can just press F9, and the menu would pop wherever the mouse is. So I can change this to a sphere. Some other weird shapes that are default. One that are interesting is this shell-like object, and then we can increase the not the subdivisions, but we can increase the thickness if we go to the modifiers, and then just increase the thickness a little bit. This is what this would look like. Maybe you can go to a different matcap. So like this. Other thing that you can do is again, you can change this. For example, this other interesting shape. Sometimes the normals do not work exactly. For that, you can check the number of subdivisions. As you increase this, it's gonna change. But in this case, this shape in particular, the normals, you would have to play with the thickness. In fact, so if you go to a negative offset or so on, then that fixes that problem. The other one I want to show, it's this Klein bottle is also very interesting. This one, it looks weird also because it depends on the number of subdivisions. If it's an even number, it doesn't work that well, but if it's an odd number, then it works really well. So this is an example of a Klein bottle. You can maybe apply a glass material to this and this is the BioBlender add-on here that I'm using, but maybe for now you can do something like a translucent material, because this is probably gonna then you can see the inside and how it works. You can also go to cycles and see how this looks. All right. Then you can also do your own input. So if I since I've done other options, then as you see, I need to go back to mesh, add XYZ again, and then we have this menu here. So for example, you can type any function of theta and phi here. For theta, you're gonna use t, and for phi, you're gonna use p. And the way you would do this is, for example, we could type here something like cosine theta, and then I don't know, for y we can do sine phi, and then we can do here I don't know, maybe cosine phi times sine theta, maybe something like that. And then to actually to actually see this, then you have to go to user input, and maybe this is kind of the shape that we get. For that, you can maybe change this to a divide sign and see what else you get. This one is really broken because it diverges. There's a 0 in sine, so it's gonna diverge. But you can still play around it. So let's go back to times. Maybe you can add 5 times this, and then you get you extend it this way. So let me actually go back to this. Other things that you can do are change the actual ranges and the levels of subdivisions. So for example, if I go to 10 levels of subdivision, I still get the general shape, and if you see there's very few geometry restraining this, so then you can go ahead and maybe start, so it's not only for math visualizations, but you can also create initial topology that maybe you can edit later on. For example, if you activate proportional editing and you move this, then you get some different shapes that you can start modeling. Regarding the Klein bottle, I wanted to show something about the Klein bottle, so let me go back to the Klein bottle here. Right, so this is gonna be broken for 11. So another thing that you can change, and it works really good here, is the upper bounds. So if you change this, and I don't want to go that far, but as you see, if you go to something between pi and 2 pi, then you can get something that looks like this. You can also change the phi bound as well. As you see, it disappears this way, and you could animate this in principle and have shapes. Do not go over 2 pi because then it's just gonna repeat itself. Alright, so that's about this type of object. We can go into the next one, which is a C function. So this is similar, but it's just a grid, and then based on a grid you are plotting a function in the C axis. So in this case this will be the saddle. You can change this to for example a trigonometric function. You can extend this size y and x and get already some interesting shapes here. You could also like for example a wave. This one you can maybe increase the scale to make it more obvious, and then again you can increase the x and y. So here you get something very similar to the wave modifier, in fact, but it's just as you see, this is the underlying geometry of this. Alright, let me go ahead and try user. You can try all these modes. Exponential, it's also one. Might want to increase the scale on that one, and it looks something like this. So maybe we go down on the scale. It will actually fix this a little bit. Yeah, but you can play around with the settings. You can also modify the thickness, as you can see here. And then you can test all the ones that are here. This one is a little bit crazy. If we go down in the scale, maybe we get something that looks like that. Alright, you can also do, so the final thing is like you can also do user input. For example, if I try to type here, I don't know, and the way this one works is that you can use all these predefined functions, so exponential function, sine function. So let's say 3 times exp of, and here, as I mentioned, is a function of x and y, so you would want to type here, for example, y plus 1. You can square this with double asterisk, so square minus x square, maybe something like this. And then again you would have to change this to user input. And then as you see, if I go back in thickness and maybe I go back to 1 and 1, no, I have to give it a little bit more of this way and then a little bit more this way. So this is what we get. We can modify the scale of this curve. We can make it negative, go the other way. We can multiply this by something else, and we can just keep playing with this. For example, something like that. We could also multiply, for example, if we use a polynomial, you can also add here a polynomial, so maybe something like times, I don't know, 5x cubed cubed minus y to the 5th power, something like that. Oh, alright, so that one broke it. There's probably oh, I'm missing the time sign here. Alright, so there we go. We get something weird if we multiply by a polynomial. Maybe we can decrease the scale now. Or maybe we can make this a little bit more obvious. Maybe we multiply here by 10 times, something like that. So yeah, there we go. You make that a little bit more obvious, and then you can play with the scale again. So you can, this one actually diverges, so you have to be careful with that. But yeah, that's how you play with this. And then the last option that this has is atomic orbitals. So if you go to this orbital section, then you get something that looks like a sphere, but this is just the atomic orbital for L equals 0, M equals 0. So there's a couple of different visualization modes. Imaginary is not really going to work for that one, but you have absolute and field also. But for 0, 0, they all look pretty much the same. But if you start changing these values, then as you see, you get different atomic orbitals. So as you see, M cannot be greater than L. So as you see, this is all the atomic orbitals in this field representation. You can go back to the more common ones, such as real. So you can see here what this looks like. This is very common one, L equals 2 and M equals 0. We can go even higher. If you see some artifacts, then you can increase the level of subdivisions. Something like maybe 48, something like that. And as you see, this is what you would get. You can again play with imaginary. Is going to be very similar to real. Absolute gives something that looks like this, and you can again play with these ones, like something to get different shapes of atomic orbitals. And then field again, this one I like a lot. You can see how this one works. It gives you a sense of actual atomic orbitals. And then yeah, those are all the options. You can again play with the thickness here, but I wouldn't go that high. And then with the scale as well. But yeah, that's everything for today. And then if you like the video, please leave a like. And if you have any questions, you can also leave a comment, and make sure you subscribe to the channel for more content.